Okay, let's dive into this. We're going to try to demystify one of the most powerful tools in all of mathematics, the partial derivative. If you've ever wondered how things change in a world with more than just two dimensions, like, say, the temperature across a map or the height of a mountain, well, this is the concept that really makes it all click.
So, to get started, let's just rewind for a second. Back in basic calculus, remember how the derivative was really just a fancy word for slope? For a simple 2D line or a curve, it's super easy to see what the slope is at any given point. But what happens when we step it up a dimension?
I want you to imagine you're standing on the side of a hill, okay? Now, what's the slope right where you're standing? Well, it kind of depends, right? It depends entirely on which direction you're facing. If you look straight up the hill, the slope is crazy steep. But if you look sideways along the contour of the hill, the slope might be zero. There just isn't one single answer.
And that, right there, is the core problem in a nutshell. For a simple 2D curve, any point has exactly one slope. It's easy, but on a 3D surface, a single point has, well, an infinite number of possible slopes. And this is the exact challenge that partial derivatives were invented to solve.
So, how in the world do mathematicians deal with a problem that has infinite answers? Well, they find a really clever way to simplify it. And the solution here is just so elegant and intuitive. Instead of trying to look at all the directions at once, we're just going to look at one at a time.
Here's how the trick works. You start with your 3D surface, our hill. Then you imagine taking this giant sheet of glass and just slicing vertically right through it, say parallel to the x-axis. This slice, it creates a simple 2D curve right where it intersects the hill. And finding the slope of that 2D curve? Hey, we already know how to do that. And that slope? That is one of the partial derivatives. And that leads us right to the more formal definition. A partial derivative is just the rate of change of a function that has multiple variables. But here's the key. It's the rate of change when you let only one of those variables change, while you hold all the others perfectly still. It's literally the slope of one very specific slice of your surface.
Okay, so the concept is cool, but how do you actually calculate one of these things? This is where it gets really good, because the rule is just unbelievably simple.
The secret is this fantastic little mental trick. When you're calculating the derivative with respect to one variable, you just pretend that all the other variables, the ones you're not focused on, are just simple numbers. Seriously, just pretend they're a 5 or pi. They're just constants that are going to come along for the ride.
Let's put this into practice. It'll make it super clear. Imagine we have a function f of x and y equals x squared times y cubed. Our goal is to find its partial derivative with respect to x. So this is the math version of our slicing method. We're finding the slope, but only in the x direction. Okay, so following our pretend it's a number rule, we're going to treat that y cubed term as just some constant. We know the derivative of x squared is just 2x. So the derivative of x squared times some constant is, well, it's 2x times that constant, which means our answer is 2xy cubed. See? That y cubed just tagged along, totally unchanged.
Now, this is not just some abstract math game. It has seriously powerful real-world uses. So let's look at a practical example to see how this helps us make sense of the world around us. So here's a table showing the height of waves out in the open ocean. And as you can see, the height, which we're calling h, depends on two things, the wind speed, v, and the amount of time, t, that the wind has been blowing. Okay, now we can ask a very specific, very practical question. If we hold the time constant at exactly 15 hours, how quickly are the waves growing for every extra knot of wind speed? This is a perfect job for a partial derivative. So how do we figure that out from the table? Well, let's just focus on that 15-hour column, because we're holding time constant, right? As the wind goes from 30 to 40 knots, that's a 10-knot increase, the wave height goes from 16 to 25 feet. That's a 9-foot jump. Then, as the wind goes from 40 to 50, the height goes up by 11 feet. So a pretty good estimate for the rate of change right at 40 knots is the average of those, which is about 1 foot per knot. And the crucial point is what this number actually means. It gives us this really specific, useful insight. Under these exact conditions, if you crank up the wind by just one more knot, you can expect the waves to get about 1 foot taller. That's the power of a partial derivative right there.
So let's zoom out for a second. We've seen how they work, we've seen an example, but why is this whole one direction at a time approach so incredibly fundamental?
Well, it turns out this simple idea is the bedrock for tons of different fields. It's used to render realistic lighting in 3D graphics, to figure out how price change affects demand in economics, to forecast the weather, and it is absolutely essential for the algorithms that power pretty much all of modern machine learning.
So we managed to take this infinitely complex problem and simplify it by just looking at a couple of key directions. We found the slope facing east-west and the slope facing north-south. But that leaves us with one final, really fascinating question. How do we combine that information to find the single, steepest path up the hill?